Good afternoon, everyone. So, just like AWS likes to know who their customers are, I like to know who I have in the audience. So I'm going to take a little survey, all right, and just bear with me. So how many people in the audience before today heard of Amazon? Okay, that's pretty good. And then how many people heard of Amazon Web Services before? Still looking pretty good. And then, how about AWS IoT? How many folks have, wow, that's really a great showing. And then, the magic question is, how many folks have used AWS IoT Greengrass? Okay, so it looks like we have some work to do there. So what we're going to do today is first get a level set on what we do on the cloudy side, and then we're going to go down to the edgy side. We're going to talk about some connectivity options that we work with in order to connect to the cloud, and then what we can do to mitigate some of those failures. So when I talk to customers and partners, there's many things that come up with IoT that are challenging, but three main things typically come up in every conversation as challenges. And the first challenge is environmental challenges. And this isn't just about what we face when putting in gateways or nodes or moats, whatever you want to call it, into the place where they're going to be sensing or perpetuating data up into the cloud. This also has to do with bad actors in the environment and securing the credentials to connect to the cloud. So that's one of the main things. And the next thing that we talk to our customers and partners a lot about is power issues. Now, mainly gateways are mostly connected to direct power, but we also talk to our customers about other types of IoT devices, and many times they're battery connected. I think many people in the room understand with battery connected devices, there's some challenges and some design constraints that you have to keep in mind. But today what I'm really focused on is the connectivity piece. And with the connectivity piece, what most people are familiar with is stuff like Ethernet and Wi-Fi. But when we're talking about verticals such as smart cities and dealing with transport, we're really talking more about cellular and satellite and those type of connectivity options. And there's real challenges around those that, with the connectivity in those cases. So how do we enable that? Well, first what I'm going to do, for those folks in the room who aren't familiar with the cloudy side or what we do up in the cloud around AWS IoT, I'm going to talk about what those components are. Now, the first thing that you really need in order to connect to the cloud is an ingest point. What am I going to connect to in order to get my data up there? And the next thing I need to do is once I get my data up into the cloud, how do I get it to the right service, such as a database? And the next thing I need to worry about is these IoT devices, many times they're not connected. Like if your power goes out, what do you do to understand what the current state of your device is? How can I actually control my device with my cell phone, and then sometime later, hopefully quickly if it's connected, that it can understand what it needs to do in order to change its state? And then really what's exciting about IoT and the cloud today is taking all that data and doing something super interesting with it. And we're talking about building ML models, doing analytics, those sorts of things. So to drill down what we've done for our customers and in order to facilitate those four main things that we needed to capture was first we needed to have a way to securely connect to the cloud and then make a protocol session to the cloud in order to transfer that data. So we do require a TLS 1.2 connection in order to connect to the AWS cloud. So most times you're doing that in a headless capacity, and that requires mutual authentication. But we also accept HTTP over web, or MQTT over WebSockets and HTTPS. Then what you need to have is a way to take that data. Once you've connected and made that MQTT session up into the AWS cloud, you need to have a way to route that data. And we have a component up there for our customers called Rules Engine. And what that basically is a nice interface for our customers to act like an MQTT client on the other side of the broker. So we get to look at that data, say, OK, what topics am I listening to? Take that data off the topic and send it to some other service. Then we have the device shadow, which is enabling you to determine what the state of your device should be. And what you're able to do in that case is, for example, on your cellular phone, say, I want to turn my light bulb on. And what that does is that it sets this particular state in that shadow called a desired state. Then your device subscribes to that shadow and gets the event message down to the device and says, OK, I have to turn the light bulb on. Once it's done that actuation work, then it reports that status back up into the AWS cloud. And that also enables the device to do that in a disconnected way. So if your device happens to be down while that device shadow setting happens, when it reconnects to the cloud, it can get its current state on what it needs to be at. So it's not like a regular MQTT broker where a regular ephemeral topic where that data just gets lost if you're not connected. And then finally, there's the device registry, is where you organize all your IoT objects. So really what we want to get at today is, what are we doing at the edge? What is AWS doing at the edge in order to enable our customers to operate effectively at the edge? And when we were discussing these solutions with our customers, we kept on being asked about several tenets. How can I take, for example, what I learned up in the AWS cloud and bring that down to the edge? How can I work in a disconnected way? How can I effectively organize the objects that I want to connect to my gateway? So in order to do that, what we did is we took several of those components that we learned how to do really well up in the AWS cloud, and we brought them down to the edge. Now, there's a few that we replicated down to the edge, which is the way to connect to the gateway, the way to do device shadows, the way to do security, the way to route messages, but it's a little bit different in Greengrass, but still routing messages between all those objects and routing data back up to the cloud. But there's one component here that's pretty interesting, which is enabling you to create a programmatic environment, to write the code up in the AWS cloud and then bring that down to the edge. And it's a serverless solution called AWS Lambda. It's a compute component that enables you to write code for your gateway in hopefully one of the languages that you enjoy to write in every day. For example, Python, Java, Node, and C. You can run those functions down on hardware that you own within AWS Greengrass. And then there's, over time, we released those in our initial release of AWS Greengrass, but over time we kept on listening to our customers and we kept on adding on functions, for example, machine learning at the edge. We continue to build up those capabilities. So let's drill down a little bit further into what Greengrass offers. So in terms of local messages and routing, now what we had to do was build a facility for these devices and closed M2M networks to connect to the gateway and work with it in an effective manner, not just taking the data that we're sending to the gateway and propagating that data to the cloud, but we also needed to have a way of routing those messages to other components within AWS Greengrass. For example, that compute component, the Lambda function that I created up in the AWS cloud and deployed down to the edge, I can now just send a message from a device that's within my local network, send that to the Lambda function locally, do some compute, and then reroute that message to another device within my closed M2M network. Then what I need to do is, the capability that we built up was the ability to write those functions and deploy them to the edge. But just recently, we added additional functionality to this Lambda function that will be very interesting to you, which is the ability to run native Lambda functions so you can have much greater control over the hardware. So before that point, everything was within a container, and the hardware was pretty constrained due to security reasons. well, what we felt was security reasons. And based on listening to our customers and what they needed to do with hardware at the gateway, we opened that up so you could actually have much wider hardware access through those Lambdas. So I talked about device shadows a couple of times, about the command and control and doing things in an offline state. And one of the things that we really needed to enable with the gateway with AWS IoT Greengrass was operating in an offline state. And in order to do that effectively, we had to have the device shadow at the edge work with the AWS cloud device shadow. So if I'm on my cell phone talking to the AWS cloud saying I want my device to do X, and that device happens to be in a closed M2M network that is managed by this gateway, now I can synchronize that device shadow between the cloud and this gateway, and then those devices in the closed M2M network that has no access directly to the internet can do actuation based on that device shadow change. So next is security. Of course, we do continue to require a TLS 1.2 connection when connecting to the MQTT broker. But in terms of LoRa, that's a little bit different. So you would actually have a LoRa module that's running on the gateway, and we could use Lambda functions to listen directly to that LoRa module to get the frames off the LoRa module and then run that through AWS IoT Greengrass. So this part doesn't directly have anything to do with the LoRa case. For any MQTT client that's going to connect to AWS Greengrass, the same security constraints apply. Then next, what we need to do is enable in a constrained way local device access. Now, I just mentioned the ability for those Lambda functions to have widespread hardware access. And what we want to do is create our gateways to have the least amount of access to the system as possible to decrease your security blast radius, right? So if you do have containers enabled for your Lambdas, you can still constrain direct access to individual devices. So the next thing I want to talk about, which is the crux of the talk today, is about the network connectivity. Because gateways have to work in an offline state. They have to work effectively in an offline state. That's the whole point of having these gateways, these aggregators out in the environment. But with that comes a lot of responsibility in ensuring that you have that data integrity at the edge. So let's first talk about the type of networks that people typically use to connect to the AWS cloud. Now remember, in order to connect to the AWS cloud, you have to route that through an IP network. So when most people connect, well, when they're in enterprises or when they're in retail shops, they are connecting via some kind of border gateway, IP gateway, through Ethernet or Wi-Fi. That's what people usually do. But when you're dealing with things like agriculture and transport and mobile hospitals and stuff like that, you have to deal with other ways of connecting to the cloud, such as cellular and satellite connectivity. And with that comes a whole bunch of other challenges. But wait a second. What types of connectivity are we talking about? If I have consistent connectivity, do I always have that perfect internet connection? How many people have had a perfect internet connection? All the time. One hand. I got one hand. That's really awesome. So usually you don't. Even on really super fast networks, you don't have perfect connectivity. So you need to have a way to mitigate that, even if you have a quote-unquote super great network. And the next connectivity is controlled interval. Controlled interval many times is for things like satellite, when you know that your endpoint is going to be available at certain points of the day. That may also be the case where you want to connect to your cellular provider only in certain windows of the day. For example, when your data rates are cheap. And the next type of connectivity is uncontrolled interval connectivity. This is probably the most wicked connectivity that you could have, because it's when you're out in the environment and you have no idea what could possibly happen. And where we see this a lot is when we're dealing with transport. Now, you could be in a closed transport area such as a construction site, or you could be in a wide open transport area such as an interstate freeway. But in any case, you're going to have pockets of areas where you simply don't have any connectivity, and then all of a sudden, boop, you have connectivity. So you have to be able to mitigate that sort of problem. And then, of course, you have the controlled infrequent, where you know that you have to be in a particular spot to upload data from your gateway to some link. And in that sort of case, maybe you're docking your gateway, or for example, there was a customer I worked with for natural gas pipelines, and they were doing things with the device out in the field, and they were doing big image scans of welds. So they didn't want to propagate all that stuff over a slow network or a cellular network. They wanted to bring what was considered a gateway running AWS Greengrass back to their main hub and then upload all that rich data. And that would be the same thing, for example, if you're out on a ship that's doing scanning of the ocean floor. So you're going to have, at some point, you're going to put your gateway somewhere, it's going to notice that your gateway is there, and somehow it's going to trigger a wake up for it to turn back on the interface so you can load that data up to the cloud. So what are things that we can rely on in AWS Greengrass, and ultimately, what can we use in AWS Greengrass to mitigate a lot of this risk that I just talked about? Well, the first thing that you can do through a Lambda function is determine your link state. The way that you can determine local link state in Unix is to look at your proc file system. Now with Lambda, you basically can do anything to determine what that link state is. You may have a utility from your interface provider, the person who built your interface that's connecting to Wi-Fi or to Ethernet or to cellular. And they may have a utility to do that. But in Linux, you pretty much can just use the proc file system to determine that. And you can get the event that that file is changed, get the data from the file, and then do something interesting with that. You can either set that value to a device shadow to say if the link is to set your reported state, or you could send that data to another Lambda function to try to bring back up that interface. So you can do that directly through the Lambda function. Now, the next thing that you need to do, or you'd want to do, is manage a lot of that state through device shadows. Now, one of the interesting reasons why you would do that is this just doesn't determine link state, or you don't use that to determine link state just for your uplink up to the AWS cloud. You can use that to determine your link state of anything, including the link state of your LoRa module. So if you know that your LoRa module has gone down for whatever reason or is getting a lot of malformed data, now you have the opportunity of making that understanding through the Lambda function, setting your device state. I'm having a problem with my device, in my device shadow. That shadow gets replicated up into the AWS cloud, and you can alert service staff, for example. So that's another way to mitigate this connectivity risk is leveraging the AWS cloud to notify support staff. Now, another thing that you can do is use a built-in function within AWS Greengrass. And there's a built-in function to manage the MQTT queue. Now, this is really, really great when your network's flapping a lot or you're going in and out of cellular networks, not for huge distances, though. It used to be, before Greengrass 1.6.0, that the amount of space that you had was very limited. But since then, actually, what you're able to do is not only put the messages and queue them up within the MQTT client, that's managed by AWS Greengrass within memory, but you can configure Greengrass to actually persist that data to disk, so in the case of power failure, that data won't be lost. And I just have to speed it up a little bit here. And then finally, with controlled infrequent connectivity, for example, the case where you have transport for long distances, or you don't want to reconnect your device until you go to a specific location, you can use a system such as Redis to locally log that data and then replay it once you connect. So in many cases when I've talked to customers, Redis has become very useful in that case because all that data is stored in memory, does not impact your eMMC flash, and it's super, super fast. And not only can you use Redis to log all of your telemetry data, but you can use it for other operations as well. Now remember, Redis is not part of AWS Greengrass. Redis is something that you would install on the Linux operating system that Greengrass is also running on, and you can use Lambda to connect to that Redis instance and do all that work. But there's a couple of patterns that you can apply on that. Now, this is a structure for the logging data to ensure that all your logging data is correct and well organized. But what you would want to do, what people do many times, especially if you're doing super fast readings in your environment, is do sampling or aggregation. So you would take the data that's in the Redis database, which is just raw data, and what you can begin to do is say, okay, I'm logging this data at 10 hertz, but I really only want to take one sample a second. So you can just run a very simple operation to cleanse some of that data. The next thing that you can do is do aggregation. So if I'm doing sampling in my environment, say for example it's in a vehicle and I'm doing that at 10 hertz, then I can run a function against that Redis data and say, I want to take the average, and you could even be smarter about it. You can look for serious outliers in that data set within that second. Remove the outliers, like the big outliers, like it could be just erroneous data, and then average the rest. And you can do that all within Redis via the Lambda function. So with that, in order to work with AWS Greengrass, Greengrass runs on hardware that you own, that you operate. We have a device catalog that we use to communicate to our customers the partner solutions that we've worked with, where they've built solutions that you can use to build on top of AWS. And these are qualified devices. So you can go to that device catalog. There's LoRa devices up there, and there's Greengrass qualified devices up there as well. And the next thing that you could do is how many folks in the room actually produce devices, LoRa devices? Okay, a few. There's a device qualification program, so if you're interested in qualifying for AWS IoT Core or for AWS IoT Greengrass, you can use the device qualification program to ensure that our mutual customers know that your devices can be used to build solutions on top of AWS. And then finally, just go out and play. And this time next year, I'd love to hear from you what you've gone and built. All right, thank you.